Hello everyone, welcome again to my channel Learning from Data. This is my second video on outlier detection. In the previous video, I have discussed about outlier detection techniques for mostly normal distributions. The procedures included IQR, that is Inter-Quartile range, standard deviation, z-score, and modified z-score. To proceed forward, let's revisit the IQR method. IQR stands for Inter-Quartile range. This is demonstrated by a box plot here. The typical box plot has the lower whisker, the lower quartile, that is Q1, the median, that is Q2, the upper quartile, Q3, and the upper whisker area. It has also the minimum and the maximum value marked here. Anything above this max value is considered as an outlier, and also anything below this minimum value is also considered as an outlier. And the ranges are defined by these equations. First we need to find out the first quartile, then the third quartile, and get the interquartile range, that is Q3 minus Q1. And the upper limit is defined as Q3 plus 1.5 times IQR, and the lower limit is defined as Q1 minus 1.5 times IQR. So those are the limits for maximum and the minimum values in a box plot. The IQR method, as well as standard deviation, z-score, and modified z-score, work very well for normal or nearly normal type of distributions. However, the majority of the real-world data is not normal. Sometimes the data is skewed on the right side, which is called positively skewed data, and sometimes it is skewed on the negative side, which is called the negatively skewed data. The symmetrical data is only in the ideal case that we can have, but real-world data are mostly skewed or not normal in most cases. This means the data can have either tail on the higher side and lower side of the distribution. This type of skewed distributions are shown here, and the corresponding box plots are also shown here. You can see that for symmetrical data, the median, the Q2, is right here in the middle. But for the positively skewed data and for the negatively skewed data, the median is not at the center. So those are shifted towards the tail. That's why the IQR, that is interquartile range, will be different when we compare the skewed distribution and the symmetrical distribution. Since the IQR and other standard procedures work very well for normal data, and the real world data is not normal in most cases, we need to find some alternate ways to adjust our box plots for skewed distributions. Some proposed this semi-interquartile range, or SIQR in short. It was initially proposed to adjust the box plot of skewed distribution, but later it became evident that it doesn't support the proper adjustment of the box plot for long-tailed distributions. For example, if we want to compare one of the skewed distribution of the same Airbnb data that we talked about in part 1 and extract the price for townhouses, using the same standard IQR method provides one outlier, and SIQR results in one outlier as well. So here are the two box plots that I am talking about. The left side, the box plot came from the standard IQR method, and the right side box plot came from the SIQR method. In both cases, we have only one outlier. Therefore, it suggests that the SIQR method is not that much helping us to adjust our box plot for skewed distributions. Later, more developments were done on adjustment for box plot. Medcouples were introduced by a group of statisticians and mathematicians uh, to get the adjustment of the skewed distributions box plot. It was first introduced by Bryce et al., and they introduced the concept of Medcouples to measure the skewness of a univariate sample which has a continuous unimodal distributions, which means the parameter of interest should have one clear single peak without any overlap of another possible peak. The Medcouple is defined as the median of this function. This is called a kernel function, which takes two values xi and xj, where xi is less than xj. The kernel function, which takes two input xi and xj, is defined like this: xj minus q2 minus xi divided by xj minus xi. This definition is very much resembling the measurement of quartile skewness, which is this one: q3 minus q2 minus q2 minus q1 divided by q3 minus q1. There is also octile skewness, but I'll not go to the details of that. But these equations are very similar. So how do we define the lower limit and upper limit using Medcouples? So here is the equation for lower limit and upper limit, which is similar to the IQR method, but the multiplier for IQR is a bit modified, and we have introduced that kernel function that incorporates the Medcouples. The lower limit here is defined as q1 minus the kernel function times IQR, and upper limit is defined as q3 plus kernel function times IQR. The kernel function can be implemented either by linear or quadratic or exponential models. So there are various ways to implement this kernel function. We can calculate the values of Medcouple using Python's stats model library. That one I'm going to show you in a future video, but for now here you can see that many statisticians proposed the exponential model to have a multiplier of 1.5. The equation is shown here. We have also another variable that is a for lower limit and for the lower kernel function, and we have b here for the upper kernel function, and these values are determined by fitting the data with different values. The exponential model is deemed to be simpler compared to the quadratic or linear function because it has only one parameter to be evaluated. But in linear or quadratic model, there are multiple unknown parameters that needs to be determined. That's why I will probably show the implementation of this exponential model in a future video. But for now, you can understand that for skewed distributions, we cannot use the regular IQR method. We need to modify the box plot and probably find out some other ways to implement the box plots, because the regular or traditional method of box plot will provide some outliers which may not be outliers at all. That's why we need to modify our box plot to capture those points and make sure that those points are lying in their correct location. So the outliers must be labeled as outliers, and if not, those should be taken as regular values. And that's the whole purpose of this adjustment of the box plot. Thanks for watching.